Hello chemists, this is Miss Placino and you are watching Screencast 13.6 on electrolytic cells. Today we're going to talk about what an electrolytic cell is, how they differ from voltaic cells, and exactly what we use them for. Now if you remember, a voltaic cell is really just another term for a battery, and in a battery we're going to use spontaneous chemical reactions to produce electrical energy. An electrolytic cell is really the opposite of that. What we're going to do with an electrolytic cell is apply energy. This is a process that requires energy. We can supply this energy either by connecting to external power like a wall outlet or to a battery, and then we can force a non-spontaneous redox reaction to occur. Now you'll remember earlier in the semester we talked about non-spontaneous reactions. By definition, these are just reactions that require energy. Remember, non-spontaneous does not mean impossible. Something like photosynthesis is an excellent example of a non-spontaneous process. In order for photosynthesis to occur, plants need a source of energy, more specifically the sun. No sun, no photosynthesis. So with our electrolytic cells, we're going to be taking electrical energy, should be, I guess, a little bit more specific here, and converting it into chemical energy, in other words, forcing a non-spontaneous reaction to occur. So these types of cells really only serve a small handful of purposes. Okay, so basically what I want to do during this lesson is show you the three different applications of electrolytic cells, and two of them are very, very closely related. And then we're going to kind of break it down and talk about the overall reaction, what's actually occurring, and then the reactions that are observed at the anode and the cathode. So lots of videos today, videos inside videos, pretty crazy stuff.
The Earth's crust contains many compounds, but the compounds themselves aren't as useful to us as the elements they're made up of. This rock contains aluminium oxide.
Aluminum oxide.
Split the aluminium from the oxygen, and you have one of the world's most useful metals. You can split a compound using electricity. The idea is to pass an electric current through it, a process known as electrolysis. A circuit is set up using two carbon electrodes, an ammeter, and a power supply. The white powder is lead bromide. Switch on the power supply, and nothing happens. The ammeter reads 0. Solid.
If you remember, we talked about it when we were looking at ionic solids earlier in first semester. In order for an ionic compound to conduct electricity, it has to be in one of two phases. Hopefully you remember that the solid either has to be dissolved in water, we can have an aqueous solution, or the solid needs to be melted. That's what we call a molten salt. It's just really another way of saying a liquid salt. Whether we're molten or we are aqueous, in those cases the ions have the opportunity to move around. As a solid, the ions are not going to move, and therefore electricity cannot be conducted.
Lead bromide doesn't conduct electricity.
Yeah, what'd I tell you?
It needs to be molten. Lead bromide melts at 370 degrees Celsius. Switch on now, and a current flows. In this circuit, the electrode on the right is positive. The one on the left is negative. As electricity passes through the molten lead bromide, chemical reactions start. On the left, at the negative electrode, nothing appears to be happening. But at the positive, bubbles mean a gas is being produced. Placing small tubes around the electrodes traps any gas, making it easier to see their colour. What could the brown gas be?
Remember, we're breaking down lead bromide.
The gas is bromine. Although nothing obvious appears to be happening at the left-hand electrode, Pouring the molten lead bromide away reveals a small silvery metallic bead. This is pure lead. So, passing an electric current through molten lead bromide breaks it down into the elements lead and bromine. To work out why this happens, imagine you can see the charged particles, the ions, in the compound. There are positive lead ions and negative bromide ions. Once the power supply is switched on, the lead ions are attracted to the negative electrode. The bromide ions are attracted to the positive electrode. Lead ions pick up electrons. They lose their positive charge and form lead atoms. Bromide ions give up electrons. They lose their negative charge and become bromine atoms. These form a gas. Electrolysis of lead bromide only works when the compound is molten. Why doesn't it work when the compound is solid? Change the compound from lead bromide to zinc chloride, and the products of electrolysis will be different. What would you expect to see happening when electricity is passed through molten zinc chloride? This time, bubbles of a very pale gas appear at the positive electrode. It turns dark blue litmus paper red and bleaches it lighter. So what gas is it likely to be? Again, nothing appears to be happening at the negative electrode on the left. But pouring off the molten zinc chloride reveals a bead of pure zinc. In industry, electrolysis is carried out on a huge scale. Massive amounts of electricity are used to extract reactive metals, like aluminium, from their ore.
Okay, so in that video, they are showing us how to basically run a decomposition reaction of an ionic compound. So let's take a little bit of a closer look at what's actually happening during electrolysis. And you should have this picture, something very, very similar to it in your workbook. In this case, we've got molten sodium chloride. So molten, again, is just another word to say liquid. It's going to be extremely hot. So we've got to get sodium chloride up to its melting point in order for this to work. If you think about what's really going on here, it's just simply breaking sodium chloride apart into its elements. We know that the sodium is going to be attracted to the negatively charged electrode, and that the chloride ions are going to be attracted to the positively charged electrode. Here's our overall reaction. We've got sodium chloride decomposing into sodium and chlorine. This is definitely not a reaction that you'd want to run at home. For starters, you can't get it hot enough to melt salt. Also, you're going to be producing chlorine gas, which can be extremely irritating if it is breathed in. Now, when we talked about voltaic cells, we talked about the anode being negative and the cathode being positive. That is flipped in an electrolytic cell. So we have, the cathode is the negatively charged electrode, and the anode is the positively charged electrode. Really just the signs are changed as a convention because we're forcing the electrons in the opposite direction. I wouldn't stress too much about exactly why this happens at this point in time. You'll probably talk more about this in physics. So at the cathode, we have sodium ions turning into sodium. I'll write this over here. Na plus becoming Na0. Remember, we've got to stay balanced for mass and for charge in our half reactions. I've got a charge of +1 on the reactant side as is, a charge of 0 on the product side. So in order to balance this for charge, I need to add an electron over to the reactant side. And indeed, that's what I have for the half reaction at the cathode. See if you can figure out the half reaction at the anode on your own. All right, at the anode, we have the oxidation of chloride ions occurring. This one's a little bit trickier because we end up with Cl2. But we start off with 2 chloride ions. They're going to lose 2 electrons, and they'll form Cl2 gas. And that is our reaction at the anode. So this is a very energy-intensive process. As I said in the video, the compounds that exist in the Earth's crust usually aren't as valuable as the individual elements. So we're going to melt them down, which requires electricity, pass an electrical current through them, which obviously requires electricity, and then we can separate ionic compounds back into their original metal and nonmetal. Okay, up next we've got the electrolysis of water. This is going to be strikingly similar to what we just talked about with the electrolysis of a molten salt.
If we connect an electrolyzer filled with distilled water to a source of direct current, we can
Basically a power source.
evolution of gases. After some time, we notice that the volume of the gas released at the cathode is double that of the gas formed at the anode. To identify the gaseous products of the reaction, we collect each gas in a test tube and check its behavior in the presence of a glowing splint. Characteristic cracking sound proves that the gas released at the cathode is hydrogen. The ignition of the glowing splint is evidence that the gas collected from the anode is oxygen, which supports combustion.
All right, so we've got another really just decomposition reaction occurring here, except instead of looking at an ionic compound, we're talking about a covalently bonded molecule. So here we've got kind of the same general setup that they showed in the video. And we know that cathode, the production of hydrogen happens at the cathode, and the production of oxygen happens at the anode. So the anode, again, is going to be positive in an electrolytic cell. Right that above, and the cathode is going to be negative in our electrolytic cell. So the overall reaction is really just the decomposition of water. We've got 2 moles of water breaking down into 2 moles of hydrogen gas and 1 mole of oxygen gas. Let's see if we can write some half reactions. At the cathode, we have the reduction of hydrogen ions. So we're going to write it as this. We've got 2H plus 2 electrons will yield just hydrogen gas. If you wrote this as just H plus electron yields hydrogen, that's technically not correct, but you've got the right idea. We have to show hydrogen ions gaining electrons. At the anode, we're going to have an oxidation reaction occurring. We're going to have O2 minus being attracted to the anode. We'll take 2 O2 minus. We're going to take away a total of 4 electrons as it oxidizes to create oxygen gas. It's the same exact principles with the electrolysis of the molten salt. You've got oxidation happening at the anode, you've got reduction happening at the cathode, and as a result, you're just producing 2 pure elements. All right, put a star next to this next one in your workbook. Electroplating is probably, at least in the eyes of the New York State Regents exam anyway, the most important application of an electrolytic cell. So again, I've got a short video to show you on electroplating.
In this video, we're going to learn about electroplating. Electroplating is the process of coating one metal object with another. It works by electrolysis, which is when electricity is used to drive a chemical reaction. We're going to look at why we would want to electroplate, how it works, and various conditions that need to be considered. So why would we want to do electroplating? Metals may be electroplated for aesthetics, protection, or both. Aesthetics might involve making a metal shinier or giving it an attractive colour by coating. For example, jewellery is often plated with gold or silver.
Part of the reason that we're going to electroplate, in addition to just improving the aesthetics of the material, is it's going to save a whole lot on the cost. If instead of having like a solid piece of gold to make a ring, you can have a less expensive metal and just coat it with a gold layer or a very thin layer of gold atoms, you're going to be able to sell that jewelry for a lot less expensively than you would if it was just pure solid gold. So not only will it make metals prettier, but it's a really cost-effective means of putting a very, very thin layer of a more expensive metal on top of a more, they're called base metals.
A metal coating can be used for protection as it may help resist corrosion, rusting, or just general wear and tear. Car rims are electroplated for both shininess and protection. Chromium, commonly known as chrome, nickel, tin, zinc and cadmium are often used to plate copper, iron and steel objects. Tin cans are actually made of steel but have a thin tin coating. Ed White, the astronaut who made the first American spacewalk in 1965, was wearing a gold-plated visor to protect his eyes from the solar radiation. So how does electroplating work? An electric current is passed through a solution that conducts electricity, called an electrolyte. To create this current, two electrodes are dipped into the electrolyte solution and connected to a battery or power supply. So we end up with a setup that looks something like this. When the current is turned on, the electrodes gain a charge. The positively charged electrode is called the anode, and the negatively charged electrode is called the cathode. The electrodes in an electrolyte are carefully chosen based upon what metal you are plating with. So if you want to copper plate another metal, you will use a copper-based electrolyte solution and have a copper anode. The copper for the plating comes from the electrolyte solution, which in turn has its stock replenished by the copper anode. So let's look at copper plating as an example. We want to copper plate some brass. So we have a copper anode, a brass cathode, and a copper-based solution for the electrolyte. So copper sulfate solution. Copper sulfate solution contains blue copper ions and colourless sulfate ions. The copper ions are positively charged and so are attracted to the negatively charged brass cathode. The copper ions deposit onto the brass, producing the thin copper plate. The positively charged copper ions gain electrons, which is known as reduction. The sulfate ions are negatively charged and so are attracted to the positively charged copper anode. The current supplied to the anode causes the copper atoms to oxidize, which is lose electrons, and then dissolve into the electrolyte solution. So the copper ions move from the anode to the cathode in the solution, and the electrons move from the anode to the cathode, but along the wire.
All right.
The copper anode bar gradually dissolves to replenish the copper ions in the electrolyte solution, so the solution stays at the same concentration.
Okay, I think she's done. Okay, so in electroplating, we have kind of this really interesting thing going on where we have the same metal being both oxidized and reduced. And this is a pretty infamous New York State Regents question. And they give you a setup like this, and you usually have some object, whether it's a spoon or a key or just another strip of metal. And then you have a like a jewelry metal, maybe something like a silver or even a gold or a copper bar. The overall reaction, well, let's talk about this first. The metal itself is always going to be the anode. The thing being plated is always the cathode. So they just showed it in the video as a piece of copper that was going to eventually be deposited onto just another strip of metal. They were using brass, which is an alloy. So in the example we have here, the overall reaction looks kind of funny. We've got silver ions and silver atoms forming more silver ions and more silver atoms. Basically, what's going to happen is in your solution, you've got silver ions floating around. Once you connect the battery and you get the electrolytic cell running, you are going to force the silver atoms in the strip to oxidize. In other words, produce more Ag+ ions. As the electrons leave the strip and travel through the wire and go over to the spoon, that's going to cause a negative charge to build up on the spoon. The positively charged silver ions are going to be attracted to that negative charge. They're going to migrate over to the spoon, pick up an electron, and form a silver atom, and then deposit themselves on the spoon. So your reaction at the cathode is really just the reduction of silver ions. So the silver ions that were in solution are now going to be deposited onto the item being plated, in our example, a spoon. The opposite reaction is happening at the anode. As the silver ions are taken out of solution, they need to be replenished, and they're replenished by the oxidation of silver at the anode. So it might seem a little strange to look at the overall reactions and then what's happening at the anode and the cathode, but the cathode is taking silver out of solution and putting it onto the spoon, and at the anode we have silver ions being replenished through the oxidation of silver. I know this lesson is running a little bit long, but I want to finish up with a chart on in your workbook. So I really just want to compare and contrast voltaic and electrolytic cells. The energy transformation occurs between chemical and electrical energy. In a voltaic cell, we're taking chemical energy and we're producing electrical. I'm just going to abbreviate. In an electrolytic cell, the opposite is occurring. We're using electrical energy to force a chemical reaction to occur. So it's the opposite energy transformation. Overall, in the voltaic cell, energy is released. That's why we use batteries to generate energy. And in the electrolytic cell, you need to provide an energy source because energy is absorbed. As far as the nature of the reaction goes, in a voltaic cell, you have a spontaneous redox reaction occurring. Electrolytic, because it requires energy, you must have a non-spontaneous redox reaction occurring. Okay. In a voltaic cell, electrons are always flowing away from the anode and moving closer to the cathode. In an electrolytic cell, it's the exact same thing. Electrons are still flowing from anode to cathode. At the anode, whether we're voltaic or electrolytic, the oxidation reaction is taking place. Let's abbreviate it there. The charge of the anode is different for the voltaic and the electrolytic cell. In the voltaic cell, the anode is negative. Remember, we have anode, there's the letter N in anode, there's the letter N in negative. The electrolytic cell has a positive anode. Again, that's because we're forcing electron flow in the opposite direction. The reaction at the cathode for both voltaic and electrolytic cells is the reduction half reaction. The charge of the cathode in a voltaic cell is positive. Remember, the T in cathode kind of looks like a little plus sign. In an electrolytic cell, it is negative. So if I were you and I'm trying to commit this to memory, I would really just remember voltaic cell. We talked more about those in more detail. And just remember that the electrolytic cell is opposite when it comes to the charges only. The half reaction at each electrode and a flow of electrons are exactly the same, always from anode to cathode. Anode is the site of oxidation, cathode is the site of reduction. All right, that about wraps it up for today. Thanks for tuning in to this slightly longer than normal screencast, and I hope you found this helpful.